In the previous video, we saw that the length of the carriage has to contract in the direction of motion. That's one of the other consequences of relativity. We saw it qualitatively. What we didn't work out was how much does the length have to contract depending upon the speed, and that's what this video is about. It's about crunching the algebra to work out how much the train has to contract. Okay, so let's think about the time for the journey from the point of view of each of our two observers. First of all, thinking about from this guy's point of view, from the point of view of the observer in the carriage, what would the time be for him? Well, that's going to be t0, and because speed is distance divided by time, then time is going to be distance divided by speed. Well, it's got to go up and back again, so it's going to be 2. We're going to call this L0. We're going to call the length of the train as he measures it, because it's in his frame of reference. It's going to be the 0 frame of reference, or the O frame of reference. We're going to call that L0. That's the length of the train as he measures it, so it's going to be 2 times L0 divided by C, and that's the time that it's going to take for the event to happen in his frame of reference. So now let's consider this same event from the point of view of the person on the platform, from the observer on the platform's point of view. What is happening? Well, because it's happening in a moving frame of reference, we're going to call this the V frame of reference. The event is happening in, how would it happen for him? Well, let's break it up into two times. We've got T1 is going to be the time for the light ray to travel forward along the train. Well, remember, they don't agree upon the length, so we're not going to call this L0, we're going to call that LV. That's the length of the carriage as measured by this person down here. What's the length of it going to be? We'll just call that LV. So it's going to be the distance, it's going to be LV, but remember, the front of the carriage is running away from the light beam. It'll have moved on some distance. What distance has it moved on? Well, it'll have moved on by VT1, okay? So the distance is going to be LV plus this extra, where V is the velocity at the time, T1 all divided by C. T2, coming backwards the other way, is going to be LV minus VT2, because this time the back of the carriage is rushing to meet the light ray, and so it's going to reduce the distance that the light ray's got to travel divided by C. Okay, so let's work with these and let's rearrange these and see where they go. Well, we're going to perform a bit of algebraic murder here. It's tough, it's hard. We're going to follow through just to show that it works. Follow me with this. Let's take this one here. Multiply both sides by C. CT1 is LV plus VT1. We're going to take this term over the other side, which is going to give us CT1 minus VT1 equals LV. Take out T1 as the common factor. C minus V equals LV. T1 is going to be equal to LV on C minus V. And by a bit of symmetry, we should be able to see that T2 is going to come out as LV on C plus V. Okay, now our total time is just T1 plus T2, so TV is going to be those two added together, LV on C minus V plus LV on C plus V. We want to get them over a common denominator. We multiply the denominators together, and if you look at that, you can see that's the difference of two squares. So our denominator is going to be C squared minus V squared, and then we're going to cross multiply to get our two numerators. We're going to multiply this by this one here and vice versa. So we've got CLV plus VLV plus CLV minus VLV plus, and the minus LVs are going to cancel, and we're going to keep going with this. So that's going to give us two lots of CLV over C squared minus V squared. Well, I'm going to pull out C squared on the denominator like I did before, put C squared outside of 1 minus V squared on C squared, and it's still going to be 2CLV for the numerator. One of those C's are going to cancel, so that's going to give us 2LV on C outside of 1 minus V squared on C squared. Okay, now that equals TV. What does TV equal? Remember from our time dilation before, TV equals T0 on the square root of 1 minus V squared on C squared. So we're going to sub that in, so that gives us T0 on the square root of 1 minus V squared on C squared equals 2 LV on C outside of 1 minus V squared on C squared. Okay, now we know from before, when we first did this, that the T naught is 2L naught on C, so we're going to substitute that in over the left-hand side, so it's going to give me 2L naught on C outside of the square root of 1 minus V squared on C squared equals 2LV on outside with C outside 1 minus V squared on C squared. I told you it was death by algebra here, and I wasn't joking. So let's keep going with this one here. Okay, so now we can equate those two. We can cancel the 2's there, and I want to get the expression of LV, so I'll multiply the other side by the denominator on the right-hand side. So LV is going to be equal to C outside of 1 minus V squared on C squared, L naught, divided by C outside of 1 minus V squared on C squared. Okay, we are very nearly there. Let's cancel those C's there. And you should be able to see that we can actually cancel one of those. That's a square root on the bottom, and that's the squared term on the top. So let's square. Anyway, we should be able to cancel those. It works fairly well. So that's going to be equal to square root of 1 minus V squared on C squared L naught, and that's what LV equals. LV is that, and of course this is our term that appears in all of our Lorentz transformation, the square root of 1 minus V squared on C squared, and that's how much the length is going to contract.